the frequency counter module. I needed a very simple frequency counter. I already had 4 frequency counter. I sold 2 of them because I don't use them a lot. And if I use them, it's mainly to check out CB radios. So I need something very simple, very basic. And this is it. So I have it hooked up to a CB radio via a RF tap. I'm now transmitting channel 20, which is 27205. I can change the gate time. Sometimes I don't need all this precision. So change the gate time. Let's take another channel here. So you see, very nice. I can go to kilohertz resolution. I can also display the period. So very basic. Design based on FPGA for the counterpart, which was a bit challenging. And the input module is based on a very classic design that is used by many manufacturers from an application note from Motorola. So it can go up to 57 megahertz. The actual design is made for much more, but at 57 megahertz the output of the input module is more like a sine wave than a square wave. And I think that is causing the problems. I'm not investigating that any further. Digital wise, it can probably go much higher. But I'm happy with that. I don't need much more. Sensitivity, it can do 20 millivolts. I tested at 10 megahertz, a bit below 20 megavolt even, so that's fine. It's very sensitive. Sensitive enough for my applications. Low frequency, I tested with a very high input at about 5 hertz. Yeah, that low, from 5 hertz to 57 megahertz. And yeah, that's more than enough that I need for now. The frequency counter module. A very basic frequency counter, display, 2 rotary encoders and an input. Nothing too fancy. The design is made in 2 parts, and there's a reason for that. So we have the digital part. Let me see if I can show it a bit better. Underneath are a few components as well. We have 20 megahertz thermally compensated crystal oscillator and a very tiny Machxo2 1200 logical elements FPGA. So the counterpart is done completely in the FPGA. Which was a bit new to me. I worked with some PLDs in the 1980s, but those had like 32 cells at maximum. This one has 1200 cells. The counterpart was relatively easy, but I wanted to communicate with it, and that's done via I2C bus, and that was the biggest problem to get working. So there is a reference design from Lattice on the hardened I2C that's inside, but it was hard to get it working because it was, I'm not sure if it is a bug or something, but if I want to read some data from a register, I send a command to read 1 byte, and then I send a command to actually read that byte. And there seems to be a timeout built in to the code. So I always got, I did get my byte, but I always got zeros. And after debugging, I found out that there was some timeout occurring after like 16 clock cycles. And so because the ESP32 was probably not fast enough, so they probably tested the reference design with another FPGA board, which can do it very fast. So there's some latency between the command that is sent to read the register and the actual reading of the data, and that was causing timeout. So after changing that in the state machine, I was able to read the correct data. So that was a bit of work to get that working. The The rest is in the analog part. So I made a separate analog module. The reason being that I was not sure about the design. And luckily I did, because this was the first design. Also commonly used on the net. You can find it as a TLV3501, very fast comparator. It is documented as an input module. Some people sell it as an input module for a frequency counter. They show some nice pictures of measurements on very high frequencies, which is all fine. But if you go below 1 megahertz, then it is rubbish. You get a lot of jitter, mainly because it's simply too fast and the slope of the analog signal is too slow. So you have, on the one hand, several people who designed an input module for a frequency counter with it. You have people selling it as an input module for a frequency counter. And you also have another number of entries in forums that are discussing this. And basically these people have the same problem I had, which is a lot of jitter on low frequencies. So anything below 1 megahertz doesn't really work. So that project was scrapped. I tried the prototype, same comparator, but with a threshold, so more like a Smith trigger, same problem. So what do? You go back to a basic design, and that's based on a data sheet from Motorola from the 1970s. And in that time and later on, up to the 90s, everybody seemed to have been using the same circuit, more or less. So the 10116 ECL chip is at the heart of it. It's obsolete, but you still find plenty of them. Input buffer and some transistors to couple to the output. So I get a nice 3.3 volts up there. So it's a classic design. Some of the parts in the design are obsolete, so I had to replace the transistors by whatever is available these days. And it works. It works pretty well. As you have seen the specs in my other video, the first part of the video, it does reasonably well. I tested it. Yeah, the design goes to 57 megahertz. The analog part can do much more, but the output is more like a sine wave than a square wave. I don't think the FPGAs have no problem with that. But I'm happy with 57 megahertz for now. I will add some prescalers anyway later on. So luckily I did the board in 2 designs, otherwise I have to scrap the FPGA part and everything. I didn't want to do that, so that's why it's in a 2-part design.